How do I tell if my data is normally distributed? I get asked that question a lot by students, usually when they are writing IAs and they have a bunch of data. And the short answer is that you don't. In fact, your data is not normally distributed. Your data is a handful of points, and that is a discrete thing. The normal distribution is a continuous thing. So that's the wrong question to begin with. Here are some questions that might be better. Does the data come from a normal distribution? Has it been sampled from a normal distribution? Is the normal distribution a good model for this data? Is it a good fit for the data? So when you ask the right questions, it begins to give us a hint of what kind of things we are going to do. In particular, this last question, if the normal distribution is a good model for the data, if it's a good fit for the data, is precisely the question that we need to ask if we're going to do hypothesis testing on the data, which can be a very interesting thing. But the first thing that you might want to do with your data is just to sketch it, to visualize it, to see if it looks like a normal distribution. And normal distributions look pretty much like this. They are bell-shaped curves, and they have this kind of formula that describes this kind of curve. So the first thing that you might want to do is to graph a histogram of your data to see if it looks vaguely bell-shaped. And this is going to be easier to do the more points you have in your data. My example here is 61 points, which is not that much, but it's also not too small. So let's see what I can do with it. So I've selected the column. Now I'm going to insert a graph here. That is not the kind of graph that I want. I want a histogram. There are some things that you might want to do here, like decide on the width of the columns. Right now he is using 0.13 as a width. I don't know where he got that. Maybe you want to use 0.1, which is a rounder number, but it's making my graph look worse, isn't it? If you make the intervals too small, you start to see things that go up and down, and that is not looking very good if you want to make it look like a normal distribution. On the other hand, if you make them too large, then you don't have that many bars, which is less information visually. 0.15 is looking kind of good. So I don't know, I think I'm just gonna go with the 0.13 that Google Sheets chose automatically anyway. Okay, so the next thing that I'm going to want to do is to put the image of this histogram into GeoGebra, because I'm going to try to overlay the graph of a normal distribution on top of it. Control C, Control V onto here. And then in GeoGebra, if you get into the configurations of the image, you get to play around with these corners here to try to line up the numbers in the image with the numbers in the axis, which is going to be helpful. So for example, right now I have it a little bit too tall because the 5 is not lined up with the 5, but it's just a process of trial and error. I'm going to make this a little bit better here. So just to show you the other thing that I clicked here on what they call a basic configuration, I made it into a background image so that it's not on over the grid like this. That's better because then I can see both. And the other thing that I want to do now is to stretch the vertical axis some more. I can do that by holding down the Shift key as I drag the axis like this. So there you go. I played around with the numbers a little bit more to make it look even more perfect. And now I need to overlay a bell-shaped curve here. So from the Wikipedia website, I can see the expression of the function that I need. This is not part of the syllabus, but it's useful for IAs. And so the mu and sigma here, as usual, are the mean and standard deviation of the normal distribution that you want to graph. So you're going to type that function into GeoGebra, but first you need to figure out the numbers that you're going to use for mu and sigma, and those should come from your data. Google Sheets is going to help you calculate those things. And just be careful to use the standard deviation .s command instead of the .p. Now, I'm not really sure if AI standard level has this distinction, but AI high level certainly does, which is the standard deviation of your data versus the standard deviation of the population you believe the data came from. That's the second one that you want, right? And in Google Sheets, that is the .s. So there you go. Here are the numbers that I'm going to use for mean and standard deviation. Again, this is the formula that I want to type into GeoGebra. And there it is. I have typed it. So you see that the shape of the bell curve that he's drawing looks to be centered in the correct place, which was approximately 0.47. But it definitely looks a lot shorter than the bars in my histogram. And that is because it is scaled as a probability distribution, and the histogram is scaled as a data sample that has 61 points. So you just want to multiply your function by a number that makes it look better. And a good number to use for that would be something that makes the area of both images the same. So the area under the normal distribution is 1 by definition because it is a probability distribution. And the area of the histogram is the width of one of the bars times the number of data points that you have. So in my case, that was 0.13 was the width of the bar, and 61 was the number of points in my data set. So that's the number that I chose to multiply my normal distribution by. And this is an image that you might want to put into an IA as a first comparison. Of course, in my example, it looks really bad. They don't look similar at all, but that's just giving me a first impression that my data does not actually come from a normal distribution. Of course, this is only a subjective impression at this point, and I'm going to do a lot more things to make this into a better mathematical argument, but this is a good starting point. You have an image to put into your IA. So the next thing that you want to do with your data is to run the chi-squared goodness of fit test. And if any one thing that I'm going to say is going to be the answer to the question, how do I tell if my data is normally distributed? This is the answer. There are a lot of details that we have to talk about because you're not always going to be able to do it. But let me explain to you what this is about first. The chi-squared goodness of fit test is one type of hypothesis test. If you're taking the AI course, then you're going to know a lot about this because there are a ton of hypothesis testing that are covered in the syllabus of the AI course. And they all have a lot of things in common, but each one of them is suited for a specific type of situation. So what they all have in common to begin with is that they are meant to compare a null hypothesis with an alternative hypothesis. So null is 0, so we call them age 0 and age 1. The idea is that you take two hypotheses that are opposite to each other, and then you do some sort of calculation in order to decide which one of them is better, is more likely, is more appropriate for your data. But don't get carried away here because you are not allowed to just write whatever you want as hypothesis, okay? Each one of the tests has a very specific thing that needs to be the null hypothesis and the alternative hypothesis. And in the case of the goodness of fit test that we're going to do, the null hypothesis has to be this. It doesn't always have to be the normal distribution because you can do this for other distributions as well. But the null hypothesis is always stating that your chosen distribution is a good fit for your data. This is what you're trying to test. And the alternative hypothesis is simply that it's not a good fit. It doesn't tell you what it is. It just tells you how likely it is that the thing that you chose is the correct thing. And it's also never going to be 100% answer, okay? Because these are probabilities, these are samples, random experiments, and all of that. So there is no certainty that you can get from any of this. What you are going to get through the proper use of your calculator is a number p, which is going to represent the probability that you would find your data in the experiment that you ran, assuming that the null hypothesis is true. And I'm going to say this again because it is one of the main aspects of hypothesis testing. It's one of the things that all the tests have in common, so it's not even exclusive to the goodness of fit test. Here's the thing. You want to test if your hypothesis age 0 is likely to be true. And in order to do that, you ask a very precise probability question. It's like a conditional probability. Given that the null hypothesis age 0 is true, what is the probability that I'm going to observe these values in my experiments? And it's not even that, because if you're thinking about continuous values, there are infinitely many possibilities for what values you would observe in your experiment. So the probability of observing those precise values is always going to be zero, which is a continuous distribution thing. So the actual question is more like, given that age zero is true, what is the probability P of observing values that are at least this far off from the expected values? Because the expected values are determined by the distribution that you choose for your hypothesis. So given that that hypothesis is true, you expect to see something, and then what you observe is different. But how different is it? So the question about the P is, what is the probability of finding something that is at least this much different? This P is a number that you're going to get from your calculator, but then you're going to compare that number to something else, to a threshold, and then you're going to say, if the probability is smaller than this certain value, then it's too unlikely. I don't expect, if my null hypothesis H0 is true, I really don't expect to see this experiment result. It is very unlikely. The probability is very small. Therefore, if this did happen, this is what I got from my experiment, my conclusion is going to be that probably H0 was not true. And then the word that we use for that is that we reject H0. If the comparison went the other way around, if P was bigger than this alpha, then we would say that we do not reject H0. But what is this alpha? What is the value that we're going to compare P with in the end? This is something called the significance level, and it is said that it is very important that you decide on this number before doing the calculations or even before doing the experiment, okay? You're not supposed to just look at the final P that you get and say, this is small-ish because it's smaller than, and then you pick a number that is bigger than it. That's not the way that you're supposed to do it. You're supposed to choose the significance level beforehand, and if it happens in an exam question, of course, it's going to be chosen for you. It's going to be part of the data from the question. But if you are choosing it, you might as well choose 0.05 because that is what everybody uses. It's just a convention, okay, that a lot of scientists around the world have tended to use this particular number more and more. And all that it means, 0.05 is 5%, that we don't reject a hypothesis unless we are seeing results whose probability under that hypothesis is less than 5%. You should think about this a little bit because 6% is also very small. But if you find results that are only 6% likely to occur, you still don't reject the hypothesis. So it's kind of a weird thing. I'm not saying that you shouldn't do it this way. I'm just saying that you should be aware of the significance of what you're doing. Okay, so I said that the question about the probability P is what is the probability of finding experiment results that are at least this different from the expected values. But if you think about the kind of data that I have 61 points, and each one is a slightly different number. That is kind of a very difficult question to answer. Like, how do you even go about comparing how different it is from what you expected? What did you expect in the first place? So that is the way that we're going to do this. We're going to split the data into categories. Like in my example, all of the numbers were between 0 and 1. So I could divide them, for example, between 0 and 0.2, there are this many numbers. Between 0.2 and 0.4, there are this many numbers. And this is similar to doing a histogram like we were doing before to draw that graph. And when you do that, you are splitting your data into categories. Then you're going to calculate under the distribution from the null hypothesis H0 how many observations you would expect to be in each one of the categories. That is hopefully something easier to do. The observed values in each category are even easier because you just count from your data. And as for choosing the categories and choosing what the categories are and even how many categories there are, I still need to give you a little bit more details about the whole thing in order to answer that question. So here's the thing. When you're going to use your calculator to calculate the P given these observed values and expected values, The calculator is also going to ask you for something called DF, which stands for degrees of freedom. And the idea is that how many degrees of freedom there are starts by being the number of categories, because I could put a number here, a number here, a number here, and a number here. So I have 4 numbers to choose. But I don't have all of that freedom. So I start losing degrees of freedom for various reasons. For example, the simplest one is that the numbers in all 4 categories need to add up to the total number of observations that you have in your data. So in my case, it was 61. If I put 20, 20, 20, then automatically the last number needs to be 1. So I don't actually have 4 degrees of freedom, I only have 3. And the next degree of freedom that you're going to lose is because we took our data set and we calculated its mean value, which was something like 0.47. So when I calculate the expected values here using the normal CDF, like I've already mentioned, I am going to use that mu that I calculated from my data. So it's not like I have all of these 3 degrees of freedom that were still left here. I am losing one more because the numbers that go here need to have that mean of 0.47. So I started with 4, lost 1 for the total observations. I am losing one more because now it has to match the mean that I calculated from my data. And it's also going to have to match the standard deviation that I got from my data, because I'm going to use both of these numbers in the normal CDF. So now I am only left with 1 degree of freedom, which is really the minimum that you have. You can't fill in the boxes if you don't have freedom to choose any of the numbers. So the moral of the story is, if you're going to use a goodness of fit test with the normal distribution, you need at least 4 categories, which is why I've put 4 categories in my example table here. Now that doesn't sound like a big problem, because it's just like when I was building my histogram. I got to see variations of, like, what if I put 6 bars? What if I put 12 bars? And there are some things that begin to look strange when the bars are too short. So maybe you don't want a lot of categories, but you also can't have too few because the minimum is 4. So all of those considerations remain true here. You have to choose an appropriate number of categories. And there is one extra detail that I need to mention, which is that the numbers that are going to go into the expected value boxes, which are the numbers that are going to come from a normal CDF, these numbers have to be at least 5. This is an absolute number. It is not 5%. It is the number 5. So a conclusion that we get from this is that if we need at least 4 categories, and each category needs to have at least a 5 in its expected value, and also the total of the expected values needs to be the same as the total for the observed values, which was the first degree of freedom that we lost that I was talking about. The conclusion here is that in order to do any of this, you need at a bare minimum 20 data points. So if you run an experiment and you measure it 12 times, forget about it. You're not going to do this. You need at least 20. Lucky for me, in my example, I have 61, which is more than 20. But I want to pretend first that I only had 20, okay? I want to do the bare minimum and see what happens, and then I'm going to do it again with my actual data. So I don't know why or who decided that this number should be 5, but I've mentioned this in another video before as well. 5 is not a magic number, okay? It was an arbitrary decision that was taken that we should trust results from this kind of test starting from 5. It doesn't mean that 4.9 is absolutely useless and 5.1 is absolutely perfect. This is not how this works. It's just an approximation, and it is a convention that we don't do this with numbers less than 5. So I'm putting 4754 over there in the observed values as a made-up example, because those numbers add up to 20, and they sort of reflect what I had, a little bit more to the left of the mean than to the right. So this is a made-up example loosely based on my actual example that I was working with before. So now, let's figure out what the categories need to be here in order for my expected values to be 5555. I want it to be a normal distribution. the mean is around 0.47, and I'm trying to split it into 4 equal categories, which means that I want 25% of the observations here, 25, 25, and 25. This is exactly the kind of situation that I'm going to use the inverse normal in my calculator. So the way that I'm going to get those numbers here in my TI-84 is by using the inverse normal distribution. So I get into the distributions menu, go down to the inverse normal, and the area that I want is 25%. So I'm going to put 0, 25. The mu and the standard deviation are the numbers that I've been working with from the example, which are these. And then I'm going to run this twice, one for the left tail and another time for the right tail. Even though it is symmetric around the mean, so you could just calculate one and by symmetry find the other one. Why are you going to do that, right? It's so easy to just run it again. So these are the numbers that I just got in my calculator. I do have a little bit more significant figures, but the picture is very small. So now I'm going to write down the categories up there. And right now I have everything that I need to put in the calculator and figure out the probability under the null hypothesis of finding values such as 4754, which are this far apart from the expected values of 5555. So in order to do that, I want to get into the hypothesis testing menu, which is here in Stat, and then you go to the right twice to get to the Tests menu. There is a lot of stuff here. We're looking for the chi-squared goodness of fit test. So let's go down until we see it. Here it is. Be careful, okay? Don't get it mixed up with the chi-squared test, which is just before it. You do want the goodness of fit test for this kind of situation. Oh, but wait, I forgot to type my observed and expected values. I need to go back to the lists to type the observed values in L1 and the expected values in L2. So stat edit. So here are the values from the example that I'm currently working with. Let's go back to the goodness of fit test. So observed L1, expected L2. Let's remember that our degrees of freedom was 1, and then have it calculate. And the answer was 0.2733, which is actually quite big. So in this case, we do not reject the null hypothesis. In the made-up example, I mean. And now I want to go back to my original example with 61 data points and choose some good categories to do this same kind of test with that data to answer the question whether it comes from a normal distribution or not. And remember that the picture that we saw originally made us feel that maybe not, because it was more skewed to the right and a normal distribution is supposed to be centered. So now I want to do the same thing with my original data that had 61 points. So I can use more categories than just 4. The minimum would be 4 for the degrees of freedom reasons that I mentioned before. And with 61 points, the maximum would be 12, but then I would have all of my categories be really, really tiny, and that also doesn't feel very good. So I went with 8, which is not as small as 4, but not as big as 12. I am choosing the categories to be symmetric around the mean, so I want the 4th and 5th category to switch at 47, 44. I also want the first and the last category to be as small as possible. So I put the 5 here and the 5 over there. That's because I don't expect to have a lot of data points that far away from the mean. So I want those categories to not matter that much. And I used the inverse normal in my calculator again to figure out what number should go here and here, which are the ones that I ended up putting here. And I didn't put a percentage here. I put 5 out of 61 because I have 61 points and I want 5 of them to be here. So that is the percentage that I want to the left of the number that determines my first category. And then I thought about breaking up all the other categories equally spaced. So that gives me those numbers over there. And then to fill in the observed values line, I just have to count from my data how many of my 61 data points are in each of these categories. For example, these are the numbers between 0.3063 and 0.3903. So those are the numbers. It reflects what I remember from the original graph because it seems like the most of them are just slightly to the left of the mean. And a question that comes up a lot at this point is, what about this 2 here? Isn't it a problem because 2 is less than 5? And the answer is that no, that 2 is not a problem because that 2 is not an expected value. 2 is an observed value, and there is no restriction on what the observed values can be. It's just what you've observed. It's the expected values that can't be less than 5. So in order to fill in the expected values line, I took each category and I used the normal CDF in my calculator to figure out what is the probability of a numbered sample from the normal distribution with this mean and standard deviation being between 0.3063 and 0.3903. And I multiplied the probabilities of the categories by 61 to put it in the scale of the number of observations. And I came up with all of those numbers here. Now, again, a question that people ask a lot at this point is, what do you mean 8.81 observations? Shouldn't that be 9 observations? Well, no, it shouldn't. The expected values don't have to be whole numbers because they don't really represent the number of observations, just the average of the number of observations that you would expect to see in that category if you ran the experiment many times. So because it's an average, it can get away from the whole numbers. And if you are very, very careful here, you will see that these expected values don't quite add up to 61. They add up to 60.98. But that's just the thing with the rounding that went on along the way because of the number of significant figures that I was keeping track of. If you really want to fix that, to make sure that your expected values line does add up to 61, you're only 0.02 away. You might as well put a 1 here and a 1 there. Now we are adding up to 61. So not forgetting that this has 5 degrees of freedom because I have 8 categories and I always lose 3 degrees of freedom when I'm using normal distribution for the reasons that I mentioned before. I put all of this into the calculator and the result was P equals to 0.2141, which is also kind of big. It is definitely bigger than 5%. So the conclusion that I'm reaching here is that I am not rejecting the null hypothesis that my data comes from a normal distribution. Be careful not to conclude too emphatically that your data does come from a normal distribution, because still there's only a 20% chance of observing this data when you do come from a normal distribution. So the correct way that people tend to say this is that I do not reject the null hypothesis. Okay, so another interesting thing that I want to do with my data at this point is just a different graphical visualization of it. And this plot, the QQ plot, this is not part of the syllabus of any of the IB math courses. And honestly, I didn't even know it existed until very recently. But I thought it was cute and I want to include an example of this since I'm doing a lot of stuff with this same data set. So the idea is that you're going to be comparing two things, one in the horizontal axis and one in the vertical. And in this case, one of the things is my data points, and the other thing is a normal distribution with the mean and standard deviation that I've been working with. The idea being that if those things are a close match, then the quantiles of one distribution will match pretty much of the other distribution, and the points that I'm going to plot are going to be along the line y equals x. So it's kind of like an extreme version of doing a histogram when you're not really categorizing anything. You're just looking at each one of the data points. But it's important also to point out that this is not a hypothesis test, okay? So we're not going to be coming up with a yes or no answer from this. It's just a graphical representation. So before I go into my data, here is a totally made up example. These are just two normal distributions. They have different means and different standard deviations, but I wanted to see what happens when you plot them. And they get into a straight line, which is not the y equals x line, but it is a straight line. So that's an interesting thing that can happen to data. Maybe if you find a straight line, just not the line you were expecting, that means that your data is still normally distributed, just maybe not with the mean and standard deviation that you were expecting. So the way that I am going to do this with my data is that I am going to compare the numbers that I have, and I know there's 61 of them. So I am going to imagine that there are actually 62 tiny little ranges, because it's everybody to the left of 0.08, which is my first one, including coming from negative infinity. That's the first range, and then the second range, and so on. But then when I get to the 61st range, is everybody until 0.915. There is a 62nd range, which is everybody that is bigger than 0.915. I just don't have anything like that in my data set, but I am going to consider the range because I am comparing it to a normal distribution, which does go all the way to infinity. The command is norminv, and then first you want to give it the percentage that you were looking for, which I am going to use as rho divided by 62. It's 62 for the reasons that I was just saying, and I'm using rho, which in this cell is 1, to get 1 over 62 of the whole normal distribution. And then later when I copy paste it to the other lines, he will just use 2 over 62, 3 over 62, which is exactly what I want. And then the next parameter that I have to give it is the mean of the normal distribution that I wanted to use, which is in cell C1 right now, the 0.4744. But here I have to be careful to give it as $1, so that when I copy it to the next line, it doesn't think that I wanted to use cells C2, C3, C4, because it's not that. It's just C1. So what the $sign does there inside of Google Sheets is that it holds down that number. It doesn't change when you copy the formula to other cells. And then similarly, the standard deviation is in cell C2. So here is a $2. And there you go. He's even asking me automatically if I want to copy the whole thing. The answer is yes, please do. And you see, well, the first one was 0.08, which is good. It kind of matches my number. The second one is a little smaller than I anticipated, and they keep being smaller for a while apparently, but here, 33 and 33, that's pretty good. So that's exactly what we're going to see when we put it in a graph. We're going to see how good these things are. Of course, some points are going to be better than others. And here is the graph. It looks kind of weird. It looks like part of it is a line and another part is a different line. And I don't really want to ask Google Sheets to put a line of best fit into that because it's not going to look good. I can clearly see with my eyes that there are two different lines. So maybe instead of doing that, I put this image into GeoGebra like I did with the other one. Here, that's good enough. I don't really need it to be perfect. I just wanted to show that this part here looks like it's following one kind of normal distribution because it is on a straight line on a QQ plot with a normal distribution. And this other part here looks like it is following a different normal distribution. So this is a very interesting observation about my data that I wouldn't be able to see by just doing the goodness of fit test or the histogram like I did before. And yet it's showing up very clearly in here. So of course I couldn't resist it, and I went back to the data and did this graph based on that information. So what I did was I split the data into two parts at that point where I was seeing the two lines meet. And I calculated the mean and standard deviation for the first part, and for the second part, did the two normal distributions separately and put it over the histogram. This is what it looks like. And it's also pretty if you want to show both of them added together instead of separately. So now it looks like a distribution that is clearly not a normal distribution anymore, but it has these two distinct parts. And it fits the data quite well, which was very interesting. But that is besides the point because it's not what I want to talk about here. Instead, I want to move on and tell you what you should do in terms of the question, is my data normally distributed, if you don't have as many data points. because I mentioned before that you need at least 20 in order to run a chi-square goodness of fit test, which would really be the ideal thing to do. But say, for example, that you only have 13 data points. And this here is a subset of my original data set. I took the first one and the last one, and then every fifth point in between. So it is a systematic sample of my data set. But pretending that this is all I have, it's only 13 points. I still want to know if it's normally distributed, and now I am not allowed to do a chi-square goodness of fit test anymore. So how do I know if it's normally distributed? And here is when literally the answer is that you don't. You actually can do some hypothesis testing on this, which I am going to show you right now. But the hypothesis that's being tested is not going to be, is the normal distribution a good fit for this data, like it was in the goodness of fit test. So we're going to do a t-test on these 13 points right now. A t-test is also a type of hypothesis test, so it does have in common with the goodness of fit test the fact that we have a null hypothesis and an alternative hypothesis, that we are going to find P, the probability of the data being these 13 points, assuming that H0 is true. And then if P is very small, smaller than 0.05, we are going to reject that null hypothesis H0. But underlying that, we have an assumption that the data is normally distributed that is necessary in order to run the t-test. And I want to stress the difference between an assumption and a hypothesis, because the words can sound kind of similar, but they're really not. A hypothesis is something that you're going to test and decide yes or no whether you accept or reject that. An assumption is not going to be tested. You're not going to decide whether or not you accept an assumption. An assumption is just an assumption. That means it may or may not be true, but we are going to act as if it's true, and that's that. It can feel uncomfortable, but it's pretty safe to do in a lot of situations because most things in life are normally distributed. So the hypothesis that you're actually going to test is not whether or not this is a normal distribution, but you're going to be testing something about the mean of this normal distribution. In this case, I put my null hypothesis to be that the mean is 0.5, but 0.5 obviously doesn't have to be that. It's going to depend on your context. In my situation, since all of my data points are between 0 and 1, I felt that like 0.5 was good as a null hypothesis. I know that the mean that I calculated before from the data was closer to 0.47, but then again, it might not be 0.47 from this sample of the original data set. And I'm not even going to calculate what that is because it would be kind of a pointless test, wouldn't it? If you are already assuming that it's normal, and then you're going to test whether the mean can be the actual mean from the points that you have, that doesn't really add anything to what we know about the data. So I've chosen mean is equal to 0.5 as my null hypothesis, which means that the P that I'm going to calculate is the probability of observing these 13 data points if they are coming from a normal distribution with mean 0.5. And then as an alternative to being equal to 0.5, in this instance, I wrote that it's just not equal to 0.5. But as you will see in the calculator screen pretty soon, sometimes you can be testing whether it's bigger than 0.5 or smaller than 0.5. If you have an initial idea of whether you think it's going to be bigger or smaller, then you can use that as an alternative hypothesis. But in this case, I really don't. So I'm just going to use not equal to 0.5 as my alternative hypothesis. So like usual, the first thing that you're going to do in the calculator is get into the lists to type those numbers. Let me clear out these numbers that I'm not going to use. And now you're going to go into the stat menu again and move to the right to get to the tests. And the t-test, which is what we're doing right now, is the second one on the list. There are two basic ways to do this. The data mode is what we have. We have data points that we've added into a list. We could alternatively be doing just with stats if we didn't know the individual 13 points, but we did know that there are 13 points with such a mean and such a standard deviation and whatever. Of course, you have data, it adds more information, so it's better to do it this way. The mu0 that you want to put here is the mean from the null hypothesis that you are comparing your data to. So I'm putting 0.5, and the mean is all that we need to put in because we are assuming normal distribution, and for some reason the test does not require the standard deviation. So the list that the data is coming from is L1 where I typed it. Frequency is just one because I'm not using a second list as a frequency table, which you might be in your example. And then this line decides what the alternative hypothesis is. As I was mentioning, I'm going to leave it right here because my alternative hypothesis is just that it's not equal to 0.5. And then I'm going to go down to calculate the p is 0.68, which is still incredibly big, right? So what does that mean? It means that if the normal distribution that this came from has a mean of 0.5, then it's very easy to find these numbers. There's a 68% chance of finding numbers that are as different as this from a normal distribution with mean 0.5. So in this case, we don't reject the null hypothesis and we say, okay, the normal distribution that we are assuming could have easily had a mean of 0.5. And you see how I'm trying to be careful not to conclude that they did come from a normal distribution with mean 0.5. It's because there are many numbers that I could have tried instead of 0.5 that the answer would also have been a big P. If I try with 0.4, P is smaller, it's only 24%, but still bigger than the significance level of 5%. So I'm also not rejecting this null hypothesis. I am not rejecting either one of them because I don't have enough information to determine exactly what that was. This is what makes hypothesis testing so uncomfortable, is that you take conclusions that aren't really conclusions. But anyway, picking this 0.4 or 0.5 to use as a null hypothesis, if it's feeling uncomfortable, it's because this is not a very useful test. The t-test is actually a lot more useful when you are comparing two samples. So instead of comparing your data sample with a made-up mean like 0.5 or 0.4 that I just did, you're going to comparing two samples and asking the null hypothesis, do they come from the same normal distribution? Or you could say that you're testing whether both normal distributions that both data samples came from have the same mean. But again, if two normal distributions have the same mean, they are very likely the same normal distribution, right? As long as they have the same variance as well. So let's test this out for my data by taking a second sample from the same original data set. So for this second set of numbers, what I did in the original set was that I took the third one and then every fifth one after that, which is why I come up with one less point in the second sample because I don't have a 63. And also because I wanted to point out that this is okay. When you're doing a two-sample t-test and you want to compare two samples, they don't have to have the same size. So here I have the numbers from my second sample typed into the second list. And let's get back into the tests menu, stat, tests, and the two-sample t-test is right here. Again, you have the option of doing this with data or with stats. I'm going to keep doing it with data. The list 1 is L1, the list 2 is L2. The frequencies are both 1 because I am not using frequency tables. Again, for this case, I get the option of my alternative hypothesis being the means are different, or the second mean is bigger, or the second mean is smaller. You're going to make that decision based on what you suspect from your data. So if you think about my data, it was ordered originally in increasing order. So if from the first sample, I took points number 1, 6, 11, and then for the second sample, I took 3, 8, 13, it looks like the second sample should have a bigger mean than the first one. So I could choose this option that says that mu1 is less than mu2 as an alternative hypothesis. But then again, my first sample is bigger by 1 point, which in itself doesn't make the mean bigger, but that extra point was the biggest one in the original data set. So I am not really sure in which way one thing cancels out the other. So I'm actually going to go with this alternative hypothesis that the means are just different. I don't care which way they go. And of course, like I mentioned before, the null hypothesis is not something that you get to choose. The null hypothesis is that both means are the same. But you do get to choose whether you also want to assume that the variances are the same in this next line. I'm going to say that yes, that I am going to assume that both variances are the same, just because they are being sampled from the same larger original data set. And I also think that in the syllabus of the Math AI course, you are supposed to always answer yes for this question. So anyway, let's calculate this and see what the calculator says about the value of P, the probability of finding these two samples if they are coming from the same normal distribution, because the same variance and the same mean, which is the null hypothesis, would be they are coming from the same normal distribution. Wow, the probability is almost 100%. It is 94.6%. So that is the answer that you would get from the two sample t-tests in this example that I was just showing you. So throughout this video, I was trying to cover all things that come to my mind that one could possibly do with data that they are feeling could be normally distributed. And it is not a concrete answer. How do I tell if my data is normally distributed? It's not as simple as that. It is a very complex question. And there are many interesting things that you can do, such as I've showed you in this video. I don't know if I've showed you every possible interesting thing that you could do, but I think that's enough.